this video, we're going to continue topic 10.13, radius and interval of convergence. And we're going to talk a little bit about differentiation and integration of a power series. So all of the founding fathers of calculus, Newton, Leibniz, Euler, Lagrange, Bernoulli brothers, used power series extensively in their individual development of the subject. Because of this, we can only wonder, are the power series continuous? Are they differentiable? And can we integrate them? Because that's what we do in calculus, right? So properties of functions defined by a power series. If the function is given by what we see as a power series, this is what we defined last time, has a radius of convergence that is greater than 0, and it's on this interval where c is plus or minus r, basically. F is differentiable and therefore continuous. Moreover, the derivative and the antiderivative are as follows. So basically, we're going to follow our same derivative rules. Our exponent's going to go out front just like it always would, and we're going to subtract 1. And when we integrate, we're going to add 1, divide by the new exponent. So we're going to take the derivative and integral just as we always have. The radius of convergence is obtained by differentiating or integrating a power series is the same as that of the original series. So differentiating or integrating will not change our radius of convergence. The interval of convergence, however, may differ as a result of the behavior of the endpoint. So we might have a little bit of difference in our interval. So let's take a look at this series in this little activity. So we're given this series, n equals 0 to infinity of x to the n over n factorial. They want us to write out an expression that includes the first 5 terms of the series. So I'm just going to start plugging numbers in. So I'm going to notice I'm starting at 0. So I'm going to have x to the 0 over 0 factorial, which would be 1 over 1 or just 1. Then I'm going to have x to the first over 1 factorial, which would just be x. Then I'm going to have x to the second over 2 factorial, which would be x squared over 2. Then I would have, actually I'm going to label this f of x. Then I would have x to the third over 3 factorial, which would be x to the third over 6 if I expanded that. And then we're supposed to go 5 terms, so I'm going to go one more. X to the fourth over 4 factorial, which if I expanded that would be, in fact, I don't want to expand that. I just want to leave it in factorial, so I went a little bit too far there. Let's just call it 2 factorial, 3 factorial, 4 factorial. I'm going to go one more, x to the fifth over 5 factorial, just for good measure. All right, so that's our series. I am now going to go ahead and take the derivative of it. So f prime of x, the derivative of 1 would be 0, so I'm not going to write it down. Derivative of x would be 1. The derivative here, I'm going to bring the 2 in front, and then I'm going to have x to the first over 2 factorial still. And then I'm going to bring the 3 in front. So I'd have 3x squared over 3 times 2 times 1. I'm doing that on purpose. And then I'm going to bring the 4 in front, x to the third over 4 times 3 times 2 times 1. And then I'm going to have 5x to the fourth over 5 times 4 times 3 times 2 times 1. And I'm going to rewrite my 2 factorial as 2 times 1. So check out what happens. My pieces of my factorial here cancel. So when I write this series out, I get 1 plus x. This would be the same as saying x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. And then they want us to notice, what do we notice about the function f and f prime, and then do we recognize the function? So hopefully you notice that this function and this function basically ended up being the same thing, right? We just went down by a term. So and the function actually ends up equaling its derivative, and we know that the only function that equals its derivative is e to the x. So that means f of x equals e to the x. And if we went and looked at our expansion, this is actually the expansion for a Taylor polynomial or a Maclaurin polynomial for e to the x.